Good evening. We're here at Marshall doing our FE review. Today we're doing a review on the soil mechanics portion of the FE exam. We've got a little handout I give out to everybody called Things You Might Want to Know for the soil mechanics portion. Go through the things I think are important, kind of things I think you're going to see on the exam. And then I've also got the pages from the version 9 online manual attached to this part of this presentation, so you know exactly where the pages are coming from for soil mechanics, geotechnical engineering. It's much better than it is for the materials, because materials is spread all over the place. The geotech they do have in one concise location, so it makes it a little easier for us. So this is a sheet that I put together by just looking at what's on the exam. Nothing magical about what we see on here. There's a few things I think if you memorize, it's going to make some of those questions be real quick questions for you. Do it in just a few seconds, 10, 15 seconds. That's extra question time you can put into something else. And some of these, and most of these, you should remember from our time in class. One of the big ones is the specific gravity times the moisture content equals the saturation times the void ratio. And that one can get you a lot. You'll know you typically 2 or 3 of those real easily, and then you can use that to convert back and forth. Know the difference between dry unit weight, moist unit weight. Know that the dry unit weight is always less than the moist unit weight, is always less than the saturated unit weight. Saturated unit weight is when we have 0 air voids. All our voids are full with water, so that's where we have our definition of saturation. That's the maximum unit weight we can get for that particular soil. Moist unit weight is going to be less than that. Dry unit weight is going to be less than that. The only time you should ever truly see dry unit weights when the soil comes out of the oven. Is when the soil comes out of the oven. So you got to watch in some of these problems. They'll actually call out dry unit weight in here, and they're incorrect because there's no such thing as dry unit weight in the field. So you got to be careful with that, and you got to deal with that on the exam the best you can. Memorizing some general specific gravities. Not that they're going to ask you, what's the specific gravity for sand? But they're going to maybe ask you to calculate what's the specific gravity for this particular soil, and they're going to give you some parameters. And we got some problems we'll work that are similar to that. And when you get your answer, if you get an answer of 4 or 1, something ought to light off in your head and say, no, that's not possible. And you probably, by process of elimination, on probably 1 or 2 of the answers on each question, probably knock them off real quick and know that they can't be, because they're not anywhere between 2.65 and 2.75. So those are great things to know. Moist unit weights, and here again, most everything's going to be all in metric system, so you're talking about 16 to 20 kilonewtons per meters cubed. Moisture contents are from 6 to 20, 6 for the sands, gravels, 20s for the clays and silts. Void ratio somewhere between 0.5 and 1. So if you start getting crazy numbers, and there are materials out there that have void ratios way higher than 1, but not in the normal standard everyday things you're going to see. When you're doing your work, you always want to remember that the weight of solids, W sub S, is the constant we have. No matter what you're doing, as you're doing, the weight of solids can't change because that's a physical quantity in there. Moisture content can go up and down, and as moisture content goes up and down, the total weight can go up and down. But weight of solids is always weight of solids. Volume of solids is always the volume of solids. So that's your anchor point in all this in geotechnical engineering. The greatest and most important equation we've got, effective stress. Total stress minus the pore water pressure. We can calculate the total stress. We can calculate or measure pore water pressure. Take the difference, and that gets our effective stress for us. Effective stress controls everything in the geotechnical world. So that's why that equation is so important to us. They're not going to have you draw the diagrams we drew in class where you've got total and pore water pressure and effective stress, but they will ask you to calculate those values at different depths. So that's a good thing to know. They're not going to give you a real super complicated 3 or 4 layer soil problem like we did in class. It's probably going to be 1 soil layer, calculate the effective stress at a certain point. The water table won't be at the ground surface. It'll be some depth below the ground surface probably. And so you have to do your math as you need to get down to effective stress at the point they want. Remember, buoyant unit weight for the soil, saturated unit weight minus the unit weight of water. Some people call that gamma prime. Some people call that gamma B. You just got to go with whatever's in the book. And we'll get back to the book. There's some nomenclatures in the book different than what we learned in class. And we'll go through those so you make sure you know the difference. Permeability, everybody always loved the flow nets, right? Q equals KIA. More specifically, the equation they're going to ask you to use is K equals delta H, number of flow channels over the number of equal potential drops. They may give you a diagram, and we got the first problem we're going to work on is a diagram just like this. They're going to give you the diagram, say how many flow channels are there, how many equal potential drops are there, what's the change in height in the head across the project, and they're going to ask you to calculate Q. That's what they're going to end up calculating. I doubt very seriously you're going to see anything as complicated as this in there. Delta H, you got big delta H. Big delta H is the change in headwater to tailwater across the whole project. Where if you look at little delta H, that's that overall head loss across the project divided by the number of equal potential drops. So it's the unit drop of each equal potential drop. We get into shear strength. We got what we refer to as tau and F of the failure plane at failure. Sometimes that's just written as tau. They leave the FF off there. Cohesion plus the normal stress times the friction angle for the material. That's the classic Moore-Coulomb failure criteria. They do have that in your reference book, so it isn't something they can ask you about to utilize to solve a problem with. Got to remember sigma n, that's normal to the surface you're looking at. It's the weight of whatever's above that surface of interest. And we've got one or two problems we'll do on the sliding block that will utilize that equation. Unconfined compressive strength sometimes confuses folks because we test the sample and we'll get a sigma 1 and we'll get sigma 3 will be 0 because we don't have any confining pressure. And some people want to say that sigma 1 is equal to Q sub U, and it's not. Sigma Q sub U is 1/2 of sigma 1. And it's because of the shape of the circle there. So we're looking for the radius of the circle C. So keep that in mind if they ask you something simple about a simple shear strength test. They're not going to come in at you with C sub U tests and all those kind of things. They may come in with a direct shear test possibly because that's fairly simple. There's definitely, guarantee you 100% there's going to be some kind of earth pressure questions. Definitely going to be something like that. Rankine, and it seems like all the example problems I've ever seen, they pick on Rankine's methodology. Looking at the active or the passive earth pressures. You got to remember if we're looking at K sub A, the active state, there's a negative here. If you got K sub P, you got a plus here. It's the only difference. So P and plus.
Are the K-value tables in the manual?
No, they are not. No, they're not. And that's one of the reasons I think they like to pick on this because it's real simple. They give you the equation. They give you the equation. They do give the equation. And just remember, reasonable values for these. 0.33 to 0.5 for K sub A. Very, very common value. K sub P, 2.5 to 4. And I've got some other ones there for some friction angles, 28, 30, 35. Those are real common numbers people throw around a lot for K sub P, so it's 2.8 to 3.7. If we look at rest, we've got active, means the wall moves away from the soil. We've got passive, that means the wall is moving into the soil. Or we've got at rest, the wall can't move. The wall can't move, so that gives us this at rest condition, K naught. And the equation for that's 1 minus sine phi. And for 30 degrees, that's 0.5. So you ought to be somewhere around that 0.5 value. So when you calculate it and you come up with 0.8 or something like that for K sub A, you ought to know something doesn't smell right. And that way you can make sure you're not making foolish errors on the exam. They're going to give you here again, simple problem, a wall with one soil behind it like we've got drawn on the bottom of the diagram here. We've got a unit weight for the soil, and I have seen them give, in example problems, that unit weight is gamma D. And it's the only one they give you. So you just got to run with it. You've got no other choice. Unless they give you some other data and values where you can back calculate what the moist unit weight is. But they're not going to do that kind of thing to you. If they put a gamma D there, just run with gamma D knowing it's not 100% correct. You've got your pressure diagram. So this is the actual pressure on the back of the wall. Pressure increases with depth. And that pressure at the bottom, at a horizontal at the bottom, is K sub A. In this particular case, I'm looking at the active condition, so the wall can move away from the soil. K sub A times the height of the wall times the unit weight of the soil. And that gives me that horizontal pressure. You know, this is PSF here. That's horizontal pressure at the base of the wall. And that pressure decreases as you come up in height because H gets smaller and the pressure gets smaller. This P value is a force. Pounds. You'll be able to calculate K because you know your movement condition, either K sub A, K sub B, K naught. I almost always see them do K sub A. You know what your height is because it was given to you. You know what the unit weight because it was given to you, and 1/2 is a constant. So you can then calculate the force P on the back of the wall. So 1/3 from the base of the triangle. I've never seen them throw anything in there with water, but if it does, then K equals 1 for water. Water pressure is equal in all directions. There is no Ka, K naught, Kp condition for water. But you're absolutely going to see a earth pressure problem on there, guarantee it. Consolidation. There are good problems in the example work we've got here that you'll see. Things to remember for quickie questions. We look at this E log P curve, so we've got E log P or sigma P plotted across the bottom. As we would load the sample, moves from the upper left-hand portion of that diagram down to the lower left or lower right. The upper portion here, or the rebound portion, those are the same slope. C sub C, coefficient of consolidation, along the virgin compression zone. We've got key indicators. We've got the over-consolidated zone. That's to the left of P sub P. P sub P. We had it as sigma P. In our class, in the book, I believe they used P sub P in the reference book. That's the past pre-consolidation pressure. If you're more than that in the past, it was over-consolidated. If you are at that point, then you're normally consolidated. Normally consolidated behaviors to the right as you move down to the right. As you're coming from the left, upper left, you're in the over-consolidated region. Gives you two different equations for your settlement calculation. I have seen problems where they've asked you to calculate what C sub C is from the diagram. I have seen cases where they've given you E1, E2, P1, P2, and asked for what C sub C is. Pretty easy to do. Rule of thumb for C sub C, 0.09 times the liquid limit minus 10. If you're doing consolidation time rate work, remember HDR, the drainage path, is how far the particle of water has to travel the farthest, whichever location that is. If it's drained only at the top, it's got to go from the bottom of the layer all the way to the top. If it's drained top and bottom, it's got to go from the center, one way or the other. So make sure you keep track that HDR is different from H. HDR is different from H. I can't say that I've ever really seen a question on coefficient of consolidation. C sub V gets a little bit tricky there on some people. They do have it in the book though. It is in the reference manual. They do have the time rate dealing with the time factor T sub V, and either giving you missing one of those parameters out of there. C sub V, the time, or HDR, and having you calculate the missing component. Influence charts, they're in the book as well. So you catch the influence underneath a tank or underneath a rectangular loaded area. Say they're in the book, so make sure you're familiar with how to use those to calculate the pressure down in the ground from a surface load. Shallow foundations, they stick with the classic old Terzaghi bearing capacity equation, nice and simple. They don't have all the depth and inclination and shape factors like we're used to seeing in our classroom. So it's a much, much simpler equation. If you've got cohesion, you've got that term in there. This term is the gamma above the bearing elevation, and this is the gamma below the bearing elevation. Most of the problems I've seen them give you, though, are one soil type. So there'll be the same gamma everywhere in those. And they'll ask you, I've seen some of these review problems, they'll give you this big, laborious problem statement, and all they want to know is what's in gamma, or NQ, or NC. They'll give you all this information, and it sounds like it's going to be the problem, just horrible problem. But at the end, all they say is, what's in gamma? You go look it up in the table. You're done that quick. So it can be quite simple. Don't get too frantic when you start reading these problems, and they get very, very lengthy. Q allowables, Q ultimate divided by a factor safety. Everybody surely remembers that. Symbols. Now these are the symbols that are different in class than you're going to find in the reference manual. We used W, they use W, we use W sub T for the total weight. They use V, we use VT for total volume. They'll just throw gamma in there and not just make a distinction whether it's moist or total unit weight. They'll use gamma prime, we use gamma B. They'll use P naught for the initial stress, we'll use sigma naught in the class. They use P sub C, we use the sigma P. They use delta P for the change in load in the consolidation scenario, we use delta sigma. And they like Q sub S where we utilize Q. So all it is just difference in nomenclature. And I've got those marked in this handout we're going to see here just in a second, where those are at so you can become familiar with them. So they don't trip you up when you're taking the exam and going like, well, what's this P naught value here? Realize that's sigma naught and have those in your mind already. Classifications. They do have stuff in there to do unified soil classification and AASHTO classification. And we've got a couple problems we'll be able to do. Remember, when you're doing those classifications, they ask you if it's well graded or poorly graded. They're wanting you to do a calculation to determine that, not you look at it and eyeball it. So the big thing you're typically trying to get to do that is these D values, D60, D10s, D30s. In fact, this should be, that's D30 right there actually. I have to make that change every year. That's actually D30 right there. So you'll need D10, D30, D60, then you can calculate C sub C, C sub U, and evaluate whether it's actually a poorly graded or well-graded sample. It's just that simple. If you know how to pick those values off, you pull them real quick, it's simple math at that point, and then you can come up with a simple, quick answer to one of the questions. Put this in there to remind everybody about the gradations. Gradation size, particle size, all the way from on the right-hand side with the silts and clays, sands, gravels, cobbles. Be familiar with those sieve sizes as they move up through there. This is unified. This is the unified system, not the AASHTO system here. Here's the AASHTO system. They don't break their gravels down at all, and they only break their sands in the coarse and fine. To make sure you're aware of the differences there. Most everything you're going to get, if I've seen any problems, they give you the amount passing any particular sieve, so it doesn't really matter to you if you're thinking unified or AASHTO until they say classify it according to this, and then you just got to take the sieve sizes and run with it. So it's typically pretty simple. So here's the sheets out of the book. This is out of the version 9.2 online version you'll see out there. It's the version you're going to see on the computer when you're taking the actual exam. And there's places in here where I put on gamma M, gamma B, the terms we kind of used, to remind you that this top line is an equal potential line, that this line right here is an equal potential line. That last line that makes the soil surface before it reaches into the water, that's an equal potential drop. Each one of those vertical lines, or each one of the flow lines, as it runs down through here, There's a flow line. There's a flow line on the bottom of the weir. There's a flow line along the top of rock, along that impermeable surface. So one of the things they could ask you is, like, how many flow lines are there? How many equal potential drops are there? And I guarantee you there'll be ones where you're not counting either the bottom or the top, or you're not counting the first or the last on the drops. That answer will be there. You absolutely know it'll be there. Here's your uniformity coefficient. Here's your coefficient of curvature for doing the classifications according to Unified. All kinds of other equations for moisture content and unit weight and things of that nature there as well. Sometimes it seems like they hide some of the equations inside different little areas. Here's your equation for Q. They've got H in there instead of delta H, so we would have called that in class delta H N sub F over N sub D. We use little nf and little nd. But they just have the letter H in there for that, so be aware of that. I've never seen a seepage liquefaction question on any practice stuff, although it could be there. The right-hand or left-hand top here, we've got a compression curve like I had on my other sheet, showing where C sub C and C sub R are. RR, yeah, that sounded really good, didn't it? And we've got our different equations depending on where we start loading and where we end our loading. So you just got to follow the if, and then that tells you which equation to use. Rules of thumb like we were seeing for the C sub C. Got our effective stress, shear strength section right in there. Got your effective stress equations. Got your shear strength equation. They've got tau sub F instead of FF there. Cohesion plus the normal stress times tan phi. So you can use all those to calculate an effective stress problem or to calculate a factor of safety from a slope stability problem, which we'll see right here on this next slide over. Calculating vertical stresses, calculating horizontal stresses in the ground. So if you look at this, the equations we were using a little bit ago to calculate horizontal earth pressures are all on here. You just got to go in there and seek them out. Here's your case of A. Here's your case of P. Doesn't appear here. They're even giving you the equation for K naught. So they're going to pick one of those two conditions for movement. Like I said, every problem I've ever seen's got K sub A, it seems like. I've not seen a problem where they've given you a surcharge. I have not seen that either. Seen a lot of problems where they have the sliding block, slope failure analysis here. It's pretty straightforward if you just stop and think about it and get all your values. It's kind of odd over here. Back up 2 sheets. Here in this equation right here, they go tau sub F equals C plus sigma n tan phi. But when we come back over here, they've got this T sub FF. That's the same thing. That's the same thing. They've got their symbology a little different there. So you can calculate what the shear strength is. You can calculate what your mobilized shear strength is, and do your math and come out with a factor of safety. Like I said, we've got a problem or two that's just like that you can go through. Those start to take a little too much time, if you ask me now, because you got to calculate areas and calculate weights and all that kind of good stuff. A lot of times they try to trip you up with giving you some odd angles or something like that, and it almost seems like it's getting a little bit too long. Next, they're coming into the classification area of the manual. They give you the AASHTO classification system better. Got a couple notes written on there. The key, start on the left and work to the right and stop when you find the first one that works. If you keep going to the right, you're going to find others. Or if you start on the right, you're going to find the wrong one first. Start on the left, move to the right. On the left-hand side of this diagram, there's better soils, worse soils on the right-hand side. And they're going to give you what passes to number 10, what passes to 40, what passes to 200, the liquid limit, and the plastic limit. They're going to give you all those values. And you have to just run yourself through the chart as you move to the right till you find the right value and stop, and that's the material type that you're going to have. I have seen a few problems recently with calculating the group index. The lower the group index is, the better the number is. And here again, they're going to give you the three values. They're going to give you the percent passing. They're going to give you the liquid limit, the plastic limit, or the plasticity index. Make sure which one you're getting from them when they give it to you. And it's just a simple plug and chug there. Come up with that number. Unified soil classification systems on this sheet. Different than the table we've seen out of ASTM that we all learned with in our classes, but it still has the same information. And you've got to know whether, start off whether you've got more than 50% or less than 50% passing, or I'm sorry, less than 50%, more than 50% passing, and just work your way from left to right. Now this one you have to work all the way across. There's no quitting when you find anything. It's only one answer comes out of this table. And eventually you'll come out to a group symbol and a group name over to the far right. There's a lot of symbology here below this table that can get quite confusing. For the most part, I would think they're going to keep you in that table up to the top and not have to make a lot of other side judgments on it. Plasticity charts down at the bottom. They could have you plot a value on there and tell you, just give us a symbol. Is it CL, ML, MH, or CH? And the equations are there for each of the lines, the U line and the A line. So if you're getting close to it, you need to calculate what the actual A line value is and see how you compare it to it to see which side of that line you might be on. So that's the quickie handout I've given out for a number of years now that has a lot of the things I think you need to know. A lot of people seem to think that this review does hit pretty good on what they see on the exam. So we'll switch over now. Anybody got any questions before I click out of this? Pretty straightforward, right? Pretty straightforward. I guess I'll save that for next time, and then we'll jump back into just a Smart Notebook page here, and we'll write some problems. Some of these are going to be as simple as I'm going to read them out loud. There's just me writing anything down. Some of them are going to take a little bit of drawing, and this first one does. So I've got a sheet pile wall. I'll thin this line down just a little bit. Got a sheet pile wall. It's got water on one side. Got water on the other side. They're calling this H. And there's bedrock down here at depth. And we've got a flow net drawn. Hard to draw a flow net on this little smart screen here, but you'll get the gist of it, I think, pretty good. Pretty rough, but I think we got it there. This is actually a sand. And the sheet pile is driven in a shallow lake. The area on one side is to be pumped down as shown. The foundation is sand underlain by impervious rock. A flow net has been drawn as shown. H equals 5. 5 feet. K for the sand, 0.2 feet per minute. Feet per minute. What is the flow per lineal foot of sheet pile? Of course, that's lineal feet into the board. The answers that it gives us a choice of is 0.5 feet cubed per minute 1.0, 2.0, or 1.5. So they're wanting to know what the quantity of flow is underneath this structure. What equation we're going to whip out of our handy-dandy cheat sheet I just gave to you there? Anybody got off the top of their head?
Yeah, it's over times the
Q equals what?
K, H, and F over U.
That should be less than 1 most times. So you have fewer flow channels than you will drops. Okay, so what is K? K was given to us. 0.2 feet per minute. Pretty simple. What's delta H?
5.
Delta H is 5. It's headwater to tailwater. Headwater to tailwater. So that's 5 feet. Number of flow channels. Number of flow channels. Do I hear 5? Do I hear 5? 5 and 6, 6, 6. How many flow channels? How many distinct flow channels are flowing water underneath that structure? Bingo, right? I get right in the narrowest section and write what I want to write down. There's 1 flow channel. There's 2 flow channels. There's 3 flow channels. Flow channels. So my flow channels is 3. How many flow lines do I have? 4. Have 4. How many equal potential drops do I have? Here again, I try to pick a center flow channel and do my counting, right? So you got 1, 2, 3, 4, 5, 6. So I got 6 equal drops of pressure around through there. How many equal potential lines do I have? Got 7. 7. The difference between flow channels and flow lines is 1. Difference between equal potential drops and equal potential lines is 1. So I put 6 in the bottom here. And if I flip to the right page here real quick, we'll see that should come out to be 0.5 feet cubed per minute. If the sheet pile's excavation is 50 feet long into the board, 50 feet long in the board, what's the capacity of the pump needed to handle the flow? What's the capacity of the pump needed? So this is actually 0.5 feet cubed per minute per foot of pile. So for 1 foot into the screen, into the board, that's how much flow I'm going to get. So it wants to know if I've got a wall that's 50 feet long, how much total flow do I need to draw that down 5 feet? I'm going to take that Q times the width to get the total value. So that Q was 0.5 feet cubed per minute per foot of pile times 50 feet of pile. That's going to give me 25 feet cubed per minute. That's what that pump has got. So the Q of the pump, sorry. So that pump has got to pump 25 cubic feet per minute to draw that down that 5 feet. Real practical problem for the real world. Got this situation. How big a pump do you need to get that flow out of there? If the Q goes up by 2, the pump's got to be twice as big, right? Direct correlation. Direct correlation. If the sheet pile is extended upward to permit doubling of H, what happens to the total flow? So now H is no longer 5, it's 10 feet. H is 10 feet. So what happens to the flow? It drops by half, it doubles, it stays the same, it increases by 41%. Doubles, because all we're doing is taking H right here and doubling it, right? So it's going to double. If the sheet pile is extended downward to cut through more of the sand, what happens to the flow? It increases, it decreases, it stays the same. The solution cannot be determined. Boy, you hate them, don't you? The sheet pile is extended deeper. So I take it and I decided to drive the sheet pile down a little deeper in the ground. Does the flow decrease, increase, stay the same? Solution's undetermined.
Increase or decrease the number of flow channels if you do that?
It's not a group collective guessing game here. It actually decreases. It decreases. Because the number of flow lines is going to probably stay the same. You're probably still going to get 2 flow lines. But it's going to get more drops. It's going to decrease your flow into there. And the other thing you can kind of think about is like if so much water it's like a hose. You cut the diameter of the hose in half. If you had this kind of height here, and you reduce it down to this kind of height, only so much water can flow through there. You get more resistance, right? You get more resistance. Let's see here. Normally consolidated clay. A normally consolidated clay layer has a liquid limit of 45. The effective stress at the midpoint of the clay layer, so let's draw something up here. So here's our ground surface. At the midpoint of this layer, the effective stress is 2,000 pounds per square foot. NC, normally consolidated clay, N sub C. Estimate the compression index. Real simple equation. You guys saw it on the cheat sheet? Anybody recall what? And here again, this is the kind of thing you'll be able to get onto your screen that's got your reference manual in it, that's PDF searchable, and you'll be able to do a search and you'll be able to type in compression index, and it'll spit it out. C sub C, 0.009 times liquid limit minus 10. Yeah, one's for your reference manual to be doing your searching, and one you're working on. And then you've got your pad, your write-on pad and marker that you're using to do any hand calcs you want to do. So one side you're clicking answers, and one side you're looking stuff up, and the other side, and then you got the pad to write on. And if you do that math, 0.315 is your answer. A placement of sand fill on the surface. So now I'm going to place a sand layer up here. Sand fill on the surface is over a wide area. And it causes a vertical stress increase of 800 PSF. So delta sigma is 800 PSF. How much will the void ratio in the middle of the layer decrease due to the stress increase. If you look back at your little cheat sheet that's in your reference manual, you'll find an equation that says delta E equals C sub C, which I just had you figure out, times delta sigma times log of sigma naught. This should have had a sigma naught here, initial. You guys catch that? It should be sigma naught right there. Oh, drawing that on there wrong, guys. Sorry. Back up here a little bit. Back up here. Throw an extra parentheses in there. It shouldn't be in there. Delta sigma. Oh, geez. Back up one more. It was given to us. Problem statement given to us. Delta log delta sigma. We already figured out what's sigma C. And this is a bad problem from an exam standpoint that they wouldn't do to you, because if you mess one up, that's going to mess two up. But you'd have 0.315 times the log of 2,000 plus 800 minus the log of 2,000. It's going to give you 0.046 feet. Oh, no. Sorry. That's the change in E. There is no units there. They don't typically do that on the exam. So this is out of these practice things, out of these practice books. Let's see here. Same problem again. Oh, it should be in there, sir.
Just write it through the compression index. It's C sub C equals. You just got to redirect it.
Time rate problem from a consolidation standpoint. Got a 10-foot thick clay layer. It's drained by sand layers at the top and the bottom. So we start drawing a diagram up, and when possible, draw a diagram on any problem, not just the geotech problems, but on any problem. So we've got a clay layer, H equals 10 feet. We got sand up here, and we got sand down here. So what's that telling us? Drain both ways. So we got double drainage here. It is predicted that the total settlement will be 2 inches. So we do the math, calculate it's going to be total of 2 inches under the stress increase of a foundation load. The coefficient of consolidation, C sub V, is 0.03 feet squared per day. Question 1. The time required for 50% consolidation of the total settlement to occur is most nearly, and the answers are 640 days, 320 days, 160 days, and 80 days. So I want us to know, how long is it going to take for 50% of the settlement to occur? You guys find the time rate section of the book there? I mean, that's part of this, is looking at, that's why I give you those sheets, and so you're flipping those sheets, and so you remember where these different components are at. One of the big things we need to get is HDR, the drainage path length. We know because we have double drainage, it's going to be H over 2. 10 over 2, it's 5 feet. So we've got HDR. Two of the coefficient consolidation terms I asked you guys to memorize in class was at 50% and at 90%. So the time factor at 50% is 0.197. And you should be able to find an equation that says time factor at whatever time it is I got a cheat here. Nope, I don't have that with me. Time factor is C sub V T50 over HDR squared. You can rearrange that to get what we want to know. It wants to know how long, so it wants to know the time. So T50 is equal to the time factor 50, supposed to be a 50 there, times HDR squared over C sub V. At that point, it's crunch and run, 0.197 times 5 squared over 0.03 feet squared per day. There was feet in here. And that comes out to be 164 days when you crunch it out. So the answer is 160 days. The next question in the book is, what is it for T90? It's the same problem. It's the same problem. Find the time factor. Where's the extra sets at? Give me an extra set back there. No, it's in there. It's in there. Wow, it's not in the new one. Not going to be a question on it then. In the old version, there was actually a table of the time factors. There was an equation, a table of the time factors. Shouldn't. This is all you got. I mean, unless it's something that you perceive that any competent, halfway competent engineer ought to know off the top of their head. I mean, it was a workout problem, that kind of thing. It should be in the reference manual, right? Should be in the reference manual. Let's keep a flipping here, see what we come up with. Here we go. Do a little shear strength. We've got sand. Phi is 35 degrees. So that's a decent material. Tested in a direct shear test. The direct shear box is a 3-inch by 3-inch box, so it's a square box. And I'm going to test it with a load on the top of that of 200 pounds. So if you guys recall, the direct shear box had a box on the top, had a box on the bottom, separated by a very, very small amount of distance. Inside was the soil sample. Inside was the soil sample. We put a load on top of it, sigma n, to give us a sigma n value. And we pulled on the top, measured that force, and then we could back calculate what the friction angle of the material was. So we can look at tau is equal to sigma n tan phi. There's no cohesion in a direct shear machine. Direct shear test will be conducted properly because it's going to be conducted very slowly. There's no pore water pressure in there. There's no cohesion in there. So they told us we had a 200-pound load. We know we have a 3x3 box. Their first question is, determine the normal stress on the sample. So what's sigma n equal? They say 200 psi, 22.2 psi, 28.3 psi, or 35 psi. So we're putting a 200-pound load on top of it, and it's a 3x3 box. Simple math, right? Sigma n is the 200 pounds over 3 inch by 3 inch. That comes out to be 22.2 psi. Answer B. So that has nothing to do with geotechnical engineering whatsoever. Determine the shear stress on the sample at failure. So it wants to know what the shear stress is, so it wants to know what this value is here at failure. Tells us we can have answers of 15.6 psi, 22.2, 70, 28.3. So it's wanting to know what the shear stress is. We know we just calculate what sigma n is. That's 200. It told us what phi equals 35. No, it's not 200. 22.2, correct. Friction angle is 35. It tells you the shear stress is 15.6 psi, which was the first answer. And then to take it the next step further, we've got this force over here. What was the force that it took to move the box? So what's the shear force when the sample failed? Anybody want to take a crack at that? Well, what in the shear force? So this box has got a 3x3 area on it. 3 inches by 3 inches. And we pulled it this way by some force. We got that normal force going into the screen. So we need to now calculate what kind of value F does it need to shear that to generate shear stress of 15.6. .6 times 3 times 3. And that comes up to be 140.4 pounds. Oops. So that's that force we'd had to pull on it with to actually cause the movement to occur. We'll do a couple more here and then we'll take us a quick break, get us a little drink of water. Shallow foundations. Continuous foundation. Some of you get to cheat on this because you're in foundations class right now. The foundation is 3 feet in the ground. So d sub f is 3. In a clay, tells you the unit weight's 125 pounds per cubic foot. Says the cohesion is 1200 PSF, and it says the friction angle equals 0. And then it also goes a little farther and tells you since phi equals 0, assume n sub c equals 5.14. N sub q equals 1. So it says determine the ultimate bearing capacity. So it wants to know what little q ultimate is. So what's the equation? N sub q? Okay. N sub c times c, right? Plus what else? I don't see the bearing capacity equation in the book here. Am I missing it? That's making me scared I missed a page, guys. I don't see it there. I really don't. But it would be gamma D NQ plus 1/2 B gamma N gamma. Oh, I forgot to give you N gamma equals 0. So that's going to go to 0 there. Plug in your values. 5.14. Yep, yeah, that's a C there. 5.14 times the cohesion, 1200, plus the 125, times D, which is D sub F, which is 3, times N sub Q, which is 1. That's going to give you 6540 PSF. And technically that's per foot into the board. Factor safety is 3. Q allowable equals what? Simply the Q ultimate by the factor safety. 6540 over 3 gives you 2180 PSF.
I doubt they would have this, but if they have a 2180 and 2000, would you put the actual correct answer, or would you put, would they give the wrong?
No, you want to pick the answer that's closest to the answer you calculate. Now maybe they give you 2100, maybe they give you 2200 or something, or in this particular example problem they gave you 2180. But no, you don't want to do the thing like what you do in the real world and say, just give them 2000 and be done with
So
it.
you would pick 2200 over 2100 on that?
Yeah, I probably would. That's the closest answer, because a lot of times they'll say, what's the nearest answer, type thing. So they never give you the exact right answer. They always got to leave that little bit of doubt in your mind, right? Let's see here. Earth pressures. Hoo-yah. How about we take a break, grab a little bit of water, we're in the restroom, and then we'll continue with earth pressures here when we get back. Here. All right, so let's look at some lateral earth pressure problems, and you know they're going to be on the exam. You absolutely know that's going to be on there. So we've got a retaining wall shown in the figure. Figure looks like this. The height of it is 8 feet. Clean, dry sand. Ooh, we like that. For which the unit weight is 120 pounds per cubic foot. Phi equals 32 degrees. Calculate the active earth pressure at the base of the wall. So what's the equation for the active earth pressure at the base of the wall? Look, we all know the pressure diagram is going to look like this. It is deep. Dry sand, clean dry sand, clean dry sand. So what's the pressure at the bottom of the wall? Now he had a right to start with. So this is little p, K sub A, gamma, H, right? The gamma H is the vertical stress at the bottom, multiplied by the K sub A gives you the horizontal stress. So for this particular example, we're going to have, oh, what's K sub A? We don't know what that is yet. So what's K sub A? Minus phi over 2. What's that crunch out to be? That crunches out to be 0.307. So we're at 32. The good rule of thumb for 30 is 0.333333, so that's right about where we think it ought to be. So then we can go 0.307 times the 120 times 8. It gives us a pressure of 295 PSF. And that's per foot into the board. We don't want to forget that. Calculate the total earth force on the wall. So when they're looking for total earth force, they're looking for the big P. So that big P sub A is equal to what? 1/2. K sub A gamma H squared. So we know all those terms. 1/2 times 0.307 times 120. Oops, that's a 2 there. Times 8 squared gives us a total of 1,180 pounds per foot. We could write foot of wall if we wanted to clarify. Calculate the overturning moment per linear foot of wall due to this active earth force you just calculated. So what does it want to know? He wants to know the overturning moment. So, and I'm just going to call this point 0 right here just for no more rats. So the moment about 0 is P sub A times its moment arm. What's its moment arm? H over 3, centroid of the triangle. So we get the 1180 times 8 over 3. And that'll crunch out to be 3,140 foot-pounds per foot of wall. So they could, if they gave you the weight of the wall, or the area, the volume of the wall, and if they gave you that weight, they could ask you what's the moments resisting. They'd have to give you that moment arm, I guess. So it's just W times its moment arm. We'll call that X. You don't know what X is, so you really can't finish that out. And then they could ask, what's the factor of safety with respect to overturning? So, I mean, real simple set of steps there. It's the next problem ties onto what we just did. For the same wall shown in the previous example, assume a force is applied to the outside of the wall until passive earth pressure conditions occur. So the wall is now moving into the soil, passive earth pressures. It says calculate the earth pressure, calculate the total earth pressure. We'll just jump to that one. So the P sub P, what's that one? And and now we got to get a K sub P value. Just the other half of our equation, 45 plus, P for plus, P over 2. It's going to give us a K sub P of 3.25. That feels pretty correct to us. And when we plug that in, 1/2 times 3.25 times the 120 times the 8 squared gives us 3120 pounds per foot of wall. Nope, sorry. That's the wrong number. It's 12,480. 12,480. Pretty straightforward, pretty simple. Basics of the basics, like I say. This is a minimum competency test, guys. Minimum competency. It's not asking you to do some crazy things out there. Slope stability. So we got a little slope here to work with. That's the same. It was the same diagram, if you will. That's why H was the same, gamma was the same, all that kind of good stuff. So we've got this. Let's see. I maybe need to add on here a little bit. That's a straight line. Believe me, that's a straight line. Point A, point B, point C. They call the slope of the angle of the slope theta. We're used to calling that beta. H, they're going to give us here in a second. Got an alpha in there. A simple approach to assessing the stability of slope is to consider the statics of the weight on of the soil on A of ABC as shown in figure 1.1. The wedge slides along plane AC, inclined at angle alpha. The applied shear force parallel to the plane. So the shear force on this plane, trying to keep this thing up the hill, tau, is W sine theta. The normal force on plane AC, so the normal force on plane AC is W cosine alpha. If the soil has a shear strength parameter of C and phi, and the maximum shear force S that can be developed along that shear surface is S equals CL plus N tan phi. L is this length here now. L is the length of our surface we're sliding on. We could rewrite this if we'd like. C times L plus W cosine alpha tan phi. And we know factor of safety is equal to CL plus W cosine alpha tan phi over W sine phi. So if you refer to the figure, we assume H is 20, unit weight of the soil, write it down here, although it's for the soil we're talking about in this wedge, or in this, this triangle. Gamma is 120 pounds per cubic foot. C equals 500. PSF. Phi equals 30 degrees. Theta, slope angle, equals 26.6 degrees. And alpha equals 15 degrees. Determine the factor of safety. It says it can be 3.2, 5.7, 1.0, 1.76. You guys got the diagram? I'm going to have to slide up. I'm drawing so big. So, what is the factor of safety of that thing? Intuitively, do you have an intuitive feel for it? .2. I got one for 3.2. What else? Five's a big number. 5 is a real big number in slope stability world. Okay. So basically looking at a plug and chug to some level here. We know C is 500. L you're going to have to use geometry. You know H equals 20. You know the angle is 15 degrees. And do your math. Do your math. Oops. Slide this back down. So L is going to end up being equal to 20 over sine alpha. 77.27 feet. All this is, geometry there. So you got the 500 times the 77.3 plus the weight. How do we get the weight? Times the area, or the volume, area with the volume per. So then you got to go back and do your math again to figure out what your area is. What you'll find out is your weight ends up being 41580 pounds. So that's the total weight of that whole wedge. Here again, it's unit weight times the area times 1 foot into the board gives you your total weight. 41580 times the cosine of 15 times the tangent of 30 all over 41580 times the sine of 15. So that's what's heading down the hill. This is the driving force. This is driving. This is resisting. No, it's sine alpha because we're looking at the component this way and the component this way. What do you mean wrong equation? Oh, I do. Sine alpha. Sorry. Good catch, sir. And so that ends up telling us it's 5.7. That is a really, really high factor safety. It's a really, really high factor safety. But that's what it came out to be. Yeah, apparently. Or realistic out the window, maybe. How about that? Yeah. Let's see here. So here's a quickie. Do you know it or you don't know it? You're never going to be able to look it up. The liquid limit cup is used to determine the liquid limit is determined in the Casagrande cup method by obtaining when the number of blows is 26, 20, 25, or 10. So that's how many times we drop the cup to close the groove by a ½ inch, right? 25 for the liquid limit. No? Well, by definition, it's at 25. By definition, that's the test. When that groove closes a ½ inch, at 25 blows. At 25 blows. So either know or you don't, boom, you're quick on to the next question. Let's see here. Crazy, all these. Borrow problem. Effective stress. Effective stress. All right, so got 3 soil layers here. You guys should be able to nail this one. So I guess you're calling this point A, that point B, that point C. So clay and sand, gamma equals 18 kilonewtons per meter cubed. Gamma equals 20 kilonewtons per meter cubed. Unit weight of water, 9.81 kilonewtons per meter cubed. The effective stress at point B is, so the effective stress at B, and they give you choices of, oops. Oh, sorry. Yep, there is a water table. So they give you choices of 16.4, 36, 18, 19.6. So how are you coming up at 36, sir? Gamma times H to that depth, H to B. 18 times 2, 36. So we'll take that one. We'll take that one. The pore pressure at point C. I give you 39.2, 58.8, 19.6, or 20. How you getting that? 9 times 8.1 times the 4, 39.2. Total stress at C. Sigma C. We've got 116, 76.8, 80, 98. Say it again now. What? Run that again. What math are you using to get there? Total stress at C.
I'm going to say it's straight off. You got whole numbers for your unit weights that'll end up giving you whole numbers, not decimal numbers. And you're going to subtract 39.2, which is your core water pressure.
That might work. How would you calculate it if you couldn't deduce that?
Gamma 1, H1,
18 times 2,
plus 20 minus 9.81.
20 minus 9.81 times 4. And 11. So you are looking at 76.8. Now, the fallacy or nemesis in this problem is they give you this unit weight And you have to assume that it's saturated. You have to assume that it's saturated because it's under the water table. You have to do that. And there'll be people that'll screw that up or try to do some math somehow to come up with some other unit weight there. But it's a little simplistic in the way they present the problem. A little simplistic in the way they present the problem.
I'm kind of surprised they wouldn't give you dry and saturated.
Here again, you're thinking about my class. You're thinking about somebody who's trying to make sure you really can actually do something when you get out. They're not going to give you something that complicated. I just don't see it. I don't see it. I really don't. They've got another effective stress problem here with 3 soil layers. I don't think you guys need it. But we will go back and hit a flow net here. Got our little dam, and we've got a little sheet pile wall in front of here, and we got our ground surface here. Got a water surface up here, 7 meters. This is a 1/2 meter. And this is the soil surface, and this is also the downstream water table. Let me do a little extend here. Boy, I'm a little big. See if I can still fit this on here. That's about where I got to be from my impermeable layer here. I got bedrock down there, and this is 10 meters. It is truly impermeable for this problem, sir. It is truly permeable for this problem. K for the soil. 1 times 10 to the minus 5. Oops, centimeters. Let me zap that. Times 10 to the minus 5 centimeters per second. They've got a flow net drawn here that's, we'll see what I can do here real quick. Of course, there's going to be one dropping down here. There's one out here. There's one out here. And there's one more out here. There's one coming in here. One coming out of here. One coming out of here. 1, 2, 3. 1, 2, 3. Wow. I don't have my dam long enough. 4, 5, 6. So the dam just got longer. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 comes off the corner there. I guess I could be real slick and do this, right? Technology, right? And we've got flow lines. They come down around underneath here, back up. And this is 2 meters here to the bottom of this little sheet pile wall they got put in here. Number of head drops is number of head drops. Head drops, flow channels, and total head loss. Number of head drops, you get a choice of 3, 4, 13, or 14. Number of channels, you get 3, 4, 13, or 14. And total head loss, you get 700 centimeters, 750, 950, or 1,700. So number of head drops. Catch one of these center ones here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I heard somebody in the audience saying 13. How many flow channels? Got 1, 2, 3, 4 flow channels. What's the total head loss? $700. It's delta H, right? And that's actually the 700 centimeters, 7 meters. Head loss per head drop. Head loss per head drop. Let's move down here a little bit. So that's little delta H, right? 700 divided by 13. What's that give you? Cheat, I've got all these worked out already. 500, or 50, I'm sorry, 50 centimeters per drop. The flow rate Q under the dam. K delta H N sub flows over N sub drops. K we were given 1 times 10 to the minus 5. Delta H was the 700. Number of flows was 4. Number of drops was 13. How many drops were there? 1, 2, 3, 4, 5, 6, 7. Well, unfortunately, there was supposed to be a flow line right there, or another drop there. So actually there's 14. Sorry. I'll change the answer on you. So there's, because I'm looking at my answer and it's got 14 in it. Causing a confusion to me in my worked solution here. All right. So that should give you 0.002 centimeters cubed per second for Q. If the height of the water retained is doubled, it's doubled, right? If the sheet pile gets longer, okay. Drainage top and bottom. You guys want to do another consolidation problem? Here's a quickie though. You got a double drainage condition for consolidation. Whoa, didn't look quite that far up. You got a double drainage condition, so you got sand and sand, and you figure out what your time rate for consolidation is. And if all of a sudden this got blocked, if that got blocked, how much longer would it take, or how much time would it take for the soil to achieve the same consolidation? So you're going from double drainage to single drainage. 4 times. Man, somebody listed in class. Because it's HDR squared, right? HDR squared's in the equation. If it's double drainage, it's HDR equals H over 2. If it's single drainage, HDR equals H. So 2 squared is 4. So it changes by 4. Estimates compression index, a shallow foundation problem, earth pressure problem. Let's flip on back here. These are actually from an old FE civil pretest. So this actually came from the testing agency. An undisturbed sample. It'll take 4 times as long for the consolidation. 4 times as long for consolidation to occur. An undisturbed soil sample has a specific gravity of 2.7. The moisture content equals 10.5%. The void ratio is 0.63. The degree of saturation is most nearly. What equation do we use? One of those I told you guys need to memorize. 0.50 times 2.700. That's the kind of question you pray that's on the exam, right? Oops, times 100. 45% saturation. The answers were 25, 45, 65, or 85. Another effective stress problem, I don't think you guys need that. Another direct shear problem, you don't need that. Here's another simple quickie. If you know it, you're good to go. Which of the following is true of a normally consolidated clay? It will not settle further under the present loading condition. It appears to have been subject to previous desiccation or drying. It will settle an additional amount if the water table rises. It appears to have been subject to a greater loading condition. I got them all. You just might as well pick the other one that's not been picked. One of you will be right. Okay, let's run through them. So, materials normally consolidated. We want to, and they've got the little chart in the. They've got the chart in the manual. So we've got log of pressure. We got E. It comes over and breaks. This is our C sub C side. This is the C sub R side. This is the sigma P, the past pre-consolidation pressure. If we're on this side, we're over-consolidated. If we're at this point with today's pressures, we're normally consolidated. So let's work through these. Let's look at D first. It appears to have been subject to a greater loading condition. It would be over-consolidated, right? So right now it's the same as what we see, so it's not D. Let's look at B. It appears to have been subject to previous desiccation or drying. That causes over-consolidation. So it's not B. If the water table rises, so if we've got a situation in the ground and the water table's right down through here, and I'm looking at the stress at that point right there, if the water table goes up, does the stress at this point increase or decrease? Decreases because things are becoming buoyant, right? It's becoming buoyant. So if you look at B, B says it appears to have been subject to C. It will settle an additional amount if the water table rises. Is it going to settle or is it going to expand? It's going to expand. Got to limit itself down to D. It will not settle further under the present loading condition. So there's no additional load on it. It's going to stay at that point right there and stay as a normally consolidated sample. Another flow net problem. These are all geotech. Flexible pavement. Little flexible pavement problem. So you got a flexible pavement, and you got a surface course that's 2 inches, has a structural number of 0.44. You got an aggregate base that's 4 inches, has a structural number of 0.25. You got an aggregate sub-base that's 4 inches, has a coefficient 0.1. Structural number you're looking for is 2.50. Flexible pavement system is to be designed using the ASHTO structural number design method with the following conditions. Bingo. If the minimum thickness of the surface and aggregate base are used, the required thickness of the aggregate subbase is most nearly. So the minimum thickness of the surface and aggregate base are used. The required thickness of the aggregate subbase is most nearly. You get answers of 4 inches, 5 inches, 6.5, or 8.5. Anybody recall the structural number? Dr. Nichols covers that in transportation instead of me in geotech. Normally that falls in the geotech realm. So the structural number is the thickness of each one of these times its coefficient. Plus the 4 times 0.25 plus well, what it's got there would be 4 times 0.1. So what they're telling us is the structural number needs to be 2.5, so we're going to rearrange this 2.5 minus 2 times 0.44 minus 4 times 0.25. Divide that by the structural number for that base course, 0.10, ends up being 6.2 inches, which is going to be 6.5. Real simple, real quick. Can't beat it, right? Got one more tagged right here. They're not going to give you that problem. It's too hard a problem. Already done consolidation settlement. Here we go. We haven't done one of these. All right, a moist soil specimen has a volume of 0.15 meters cubed and weighs 2.83 kilonewtons. Moisture content was determined to be 12%, and the specific gravity was 2.69. What they want to know is what's gamma, what's gamma D, what's E, and what's S. Now you've got those equations in your reference manual. All those are right there on that first page, 142. So what's the unit weight? 2.83, 0.15, 18.87 kilonewtons per meter cubed. What's the dry unit weight? 18.87 over 1 plus 0.12. 16.85 kilonewtons per meters cubed. What's E? I don't know. They don't give you the equation to actually be able to do that. In the book here. Easiest way to get there is, you know, gamma D is equal to G gamma W over 1 plus E. And rearrange that. Rearrange that. Because you know gamma D, you know what G sub S is. You always don't know what unit weight of water is. So if you rearrange that, you get E equals G sub S gamma W over gamma D minus 1. Plug into that, you get 0.566. And S, we've already used that one already, right? S is equal to what? Moisture content G sub S over E times 100. Plug into that, you get 57.03%. Another flow net problem. I think you guys are doing pretty good on the flow nets. I don't think we need to worry about those again. That's that one. Here's classification one. Those would be pretty good. We haven't done any of those yet. Soil has the following characteristics. Fines equals 69%. Liquid limit equals 72. Plastic limit equals 48. Using the unified soil classification system, what is this soil classification? GW, ML, MH, CH. Which one of those can you cross off in a third of a second? GW. It's not a well-graded gravel, right? It's not a well-graded gravel. What other one can you cross off real fast? Remember your plasticity chart, right? Got this little box zone down here, and this flows up through here. It looks like that. What's that number right there? 50. That's 50. So this is the MLs down here. This is the CLs up here, CHs and MHs. This is liquid limit down here. This is plasticity index up through here. So we know it can't be a CL or ML because the liquid limit's 72. So we already crossed the ML off there. Now we just got to decide whether it's CH or MH. And all you got to do is calculate what the PI is. 72 minus 48. And plot your point. And it's going to plot up here in the CH zone. That's one of those simple ones you pray you get. And do it real quick. Oh, another classification one. I like it. Sample has the following characteristics. Percent passing, the number 40, 95%. Percent passing, the number 50, I'm sorry, the number 200. Uh-oh. The number 200 is 57%. Liquid limit equals 37. Plastic limit equals 18. What is the AASHTO classification? Whip out your... The only way, the best way to do this one is you guys to work your way through the table. Work your way through the table on page 145. Work your way through there and see if you can tell me what this is going to classify as. Well, give me an A number here, right? Give me an A number here. Oh, no, wait a minute. No, it is A6, yeah. I'm looking at the wrong problem, sorry. It is A6. You guys see how to get that? So you got to work your way from, and the secret's to work all the way from start over the other side under the A1s. The number 40, 57. No, yeah, it's supposed to be 57 right there. 57. So you start off, you got 95%. So none of the A1s or A3s work. Well, A3 would work, but for A3, number 200 has to be less than 10%. We got 57%. So you keep moving to the right. All your A2s will not work because we have 57% and the max can be 35%. So you're already down to 4, 5, 6, or 7. A4, 5, 6, or 7. Because we have you need to be greater than 36, and we are. You jump into the liquid limit. Our liquid limit is 37, so it only works for A4 or A6. And we look at our plasticity index. Our plasticity index is greater than 11, so that's where we get the A6 at. The second part of that problem is calculating the group index. Surely you can do that simple little bit of math. The lines in a graphical seepage flow net intersect to form a pattern of what? Triangles, trapezoids, squares, or rectangles? Squares. The flow net is constructed of equal potential and aquicludes, equal potential and flow lines, and isochrones. Equal potential lines and flow lines. A granular soil tends to densify and settle if subject to vibration and seismic shaking. When the saturated granular soil undergoes seismic vibration, they become subject to cyclic shear deformation, which causes an increase in pore water pressure. The result usually is a severe reduction in effective stress. This hazardous soil condition is called consolidation, liquefaction, heaving, or boiling. It's a whole bunch of, and the more you read it, the more you go like, oh my gosh, I have no idea what you're talking about. And then you get to the end, it's like, oh yeah, liquefaction.
It's worse if someone else is reading it to you.
Well, and it is. It's a whole lot easier, but I don't want to put these on the screen because then that becomes kind of illegal. I can read them out of the book and read them to you, but I can't. If I put them up there, I get in trouble potentially. Not that I think anybody's really going to get too crazy on what we do in a review session, but we don't want to take a chance. Foundation problems, you guys got that already. Retaining walls, you know how to do active and passive earth pressures. Getting down to the end. For the purpose of calculating the maximum stress in a braced cut in clay, what are the primary factors in determining the shape of the pressure distribution? Lateral earth pressure coefficient. Let me write these down. There's a whole bunch of them. So the lateral earth pressure coefficient, unit weight and height, unit weight, height, and cohesion, height, soil shear strength, and weight, or friction angle, lateral earth pressure coefficient, and cohesion. A braced, for the purpose of calculating the maximum stress in a braced cut in clay, what are the primary factors in determining the shape of the pressure distribution? The lateral earth pressure coefficient, the unit weight, and the cut depth, the unit weight, the cut depth, and cohesion, the cut depth, the shear strength of the soil, and the unit weight, or the friction angle, lateral earth pressure coefficient, and cohesion. Now, if you hadn't had foundations class, this was going to be a rough one. But we're in clay. Correct. So we can get rid of that one. What other thing did we say that happens with brace excavations that the reason we can't use lateral earth pressure coefficients? Brace excavations move about the top of the wall, right? Not about the bottom of the wall. So we're not going to be using lateral earth pressure coefficients. So it's the unit weight, the height, and the cohesion, or the height, the shear strength, and the unit weight. So it's going to be B. Remember those three diagrams we had? PEX diagrams? So it's going to be B. And if you hadn't had foundations class, your best bet's to pick your favorite letter. And yeah. Well, yeah. In the normal or the stereotypical clays we do doing what we're doing in class, that kind of thing. That's all the problems I got, guys. Any questions, anything specific you want to maybe try to answer? Usually takes right at about 2 hours, and that's about where we're at. If we've got no questions, we'll close it out. Thanks for showing up. Hopefully this helps you a tremendous amount. Our passage rate has been great in this exam, and it's been really good on the geotech side. So keep my streak alive, please.